In this lesson, we're going to be talking about the notation, the statistical model, the Anova, variance components, all for a split plot design. In our last lesson, we were really focused on understanding what the EUs and how we randomize for a split plot design was or is. And so let's just recall that in a split plot design, we have two types of experimental units. We have the whole plot and we have the subplot. So since we have two EUs, we're going to have two levels of randomization. We're going to have our first randomization is applying the levels of A to the whole plot. And then the second randomization is applying the levels of B to these subplots within each whole plot. Okay. Now, again, as we start to learn about more designs of experiments, we can start comparing and contrasting how designs are alike. So let's talk about the difference between a whole plot versus a block. So a whole plot acts like a block in the fact that we randomize within each whole plot. But a whole plot is not a block, okay? It acts like a block, but it is not a block. And the reason it's not a block is because we are applying a randomization at the whole level, okay? So what I mean by that is if we took our RCBD design, so in an RCB design, we had a block, maybe two blocks, where these blocks were in a treatment, they were just some type of, they were implemented due to some source of variability. We were trying to block for an extra source of variability, and we apply our treatments. In a split plot design, we have a whole plot in which we're applying a treatment, maybe A1, and a treatment, maybe A2, and then within it, we apply a second treatment. We'll change the color, a second treatment 1 through B, second treatment 1 through B. So that's how they're different. They seem similar because yes, we're randomizing within the block or the whole plot, but they're not the same because we are randomizing a treatment to the whole plot. We can have a blocking factor, so we could have our whole plots nested within a blocking factor like we saw at the end with a split plot design with a block. Okay, now recall from lesson 11, we started talking about nested designs and having that hierarchy of factors. So let's talk about and compare split plots and nested design and see if they're the same. So they're the same in the sense that there is a hierarchy and level B is nested in level A. So level B would be our subplots for our split plot and A would be the whole plot. But a split plot design is not a nested design because the levels of B are comparable across levels of A. That is, if we recall back in lesson 11, we were talking about factories and operators. And the idea was that the operator or a particular operator only worked at a specific plant. And that operator was not changing or going to the other factories. In a split plot design, in our agricultural example, we have the same soybean variety across all the whole plot. So we're looking at variety 1, 2, 3, through all of the whole plots. So a split plot is not a nested design, even though we have a hierarchy of factors. Okay? So recall our agricultural example where we have 3 varieties of soybeans, 2 types of fertilizer. In our example, we're going to be treating it as a fixed effect. We could have been random, but I decided why not do a fixed effect? It won't matter in our case. We have a balanced design. In our last lesson, we showed that this would be our randomization scheme because we're going to have blocks. So let's add some terminology to this. So factor A is going to have A fixed levels. It could have been A randomly selected levels, but again, where this is going to be our fertilizer in our example. And then factor B is we have B fixed effects. This is going to be our soybeans or our variety. We have N replicates for each level combination, so we have our total number of EUs. I provided us with the summary statistics where Yij is going to represent the ith level of A, the jth level of B, and K is going to be, in our case, represent the block or the farm we're at. But if we didn't have blocks, it would just represent the replication or the replicate of the ith level of A and the jth level. Okay, so let's start talking about our statistical model for a split plot design. So again, we have our grand mean. This is common. What we have here, this row corresponds to our block, our blocking factor, or our replication if we were just doing replication. This is our farm in our example. We also have alpha I, which represents the whole plot treatment factor. And we have our first error term, delta IK, which is going to be the whole plot error. So error term, but it's going to be the whole plot. Okay, so we have inference at the whole plot level, and that's going to be represented by these three terms. Again, remember that the whole plot level is going to be the hard to change factor. We also have inference at the subplot level, which is the factor that is easy to change. The subplot levels are going to be represented with B, which is our treatments of B. Our interaction term, the interaction is at the subplot level, which is important to note because as we start to look at our analysis and trying to figure out what f-test we need to do, I mean, when we look at our expected mean squareds to figure out what our denominator is, this is going to become important. So it's going to help us to decide if we need the whole plot error or the subplot error. And then we have our second error term, which we call our subplot error term, which is also, surprise, surprise, random. So this is our subplot error. And this is going to have us, this is performing inference at the subplot level. With the subplot design, we want to be able to recognize the key point with subplot is being able to recognize that we have a hard to change factor, which then makes us implement these two levels of randomizations. Once we understand that and recognize that, hey, we are in a split plot design, we now need to figure out and understand our tests how to test at the whole plot and subplot level. So with that in mind, let's talk about, surprise, surprise, our Anova table and our expected mean squareds. In our case, again, we're going to be using blocks, but if you don't have blocks, it's just going to be replicates. We have our sums of squareds for our whole plot and our whole plot error. I kind of made this black line right here to help distinguish the difference in our head, that this inference is done at the whole plot, this inference is done at the subplot. And so our next question we want to ask, and as you can see, is we don't have our F tests. And so we want to be able to figure out what denominator we're using for each of our tests. So when we're trying to test for the whole plot, i.e. our A, our hypotheses would look something like this for a fixed effect. Alpha equal to 0 for all of them versus not equal to 0 for some. If we come here and we look at our expected mean squareds, we know under the null hypothesis that this term would cancel out to 0, and we would be left with this term. And we can notice that this term matches with the MSE of the whole plot. And so this tells us that we'd be looking for our f-test would be MSA, or MS of our whole plot, divided by our MSE of our whole plot, which makes sense intuitively, hopefully. When we're looking at our subplot, down here, we can also test for the factor of the interaction between A, B, and our factor B. So scroll back up here. For our interaction term, notice that this right here would go to 0 under the null, leaving us with sigma squared epsilon. We see sigma squared epsilon. Same idea for our subplot. This term right here would cancel out and we're left with just the sigma squared epsilon. So this gives us the intuition that, hey, our F statistic is going to be MSAB over the MS of the subplot and MSB over the MSE of the subplot. So when we're testing for the whole plot, key point, when we're testing for the whole plot, our denominator is the MSE of the whole plot. And when we're testing for the interaction or factor B, the subplot, our denominator is our subplot error. Now, since we are in a fixed, and in this example, we are in a fixed effects analysis, we want to follow the similar protocol that we've done for the past fixed effects, which is we want to test interaction first, and then we can move on to our main effects. So we would want to test interaction first and then move on. Before going on and talking about extensions and applying this to our specific example, I want to talk about our variance components. So recall we had our this was our statistical model where we had a whole plot error and we had a subplot error. And one thing we might want to do is estimate these two variance components. Okay. In order to do that, we need to go back to our Anova table and pull off two important pieces of information. The first important information is that the expected value of the MSE of the whole plot is equal to, let's just bring this back so I can show you what we're looking at. The expected value of the the whole plot is sigma squared epsilon plus b times sigma squared delta. Okay, the other thing is the expected value of MSE of the subplot is equal to sigma squared epsilon. So if we were to estimate sigma squared epsilon, which is denoted with sigma squared epsilon hat, our estimate, our best estimate would be MSE of our subplot. Easy. Okay, now if we're interested in looking at what the expected, our estimate of sigma squared delta is, all we're going to do is we're going to look at it through this way. So we take our our expected MSE of our whole plot is going to be equal to the expected MSE of our subplot plus B sigma squared delta. All I did was took this value and plugged it into here. Now what we're going to do is we're going to solve for sigma squared delta, and we would get this. Now to find the estimate, we drop the expectations. So the estimate for our variance for our whole plots would be equal to MSE of the whole plot minus MSE of the subplot divided by B. All right. Notice whenever we've talked about variance components that sometimes they could be negative. So what could happen mathematically is that our MSE of our whole plot is smaller than our MSE of our subplot, and which would cause this variance term to be negative. If that happens, all we do is set our sigma squared delta equal to 0, and we treat it as negligible. All right. Just like other designs we've had, there are extensions to split plot designs. Here we have a split plot design, so we can account for 3 factors. So we'll have our whole plot, which is hard to change, and then maybe we have another factor that's easier to change than factor A, but harder to change than factor B. So we have another plot, and then within this plot, we split it again. We could also have a split block design where the treatments are applied in strips, as seen here. There's a lot of extensions. It just depends on what you need for your design of experiment. And again, when you're designing these experiments, it's done prior to collecting your data. And the main thing is that with split plot designs, there is going to be some restriction on your randomization, and that's important. With that, we're going to move on and look specifically at our agricultural example in our next lesson.